Good afternoon, ladies and gentlemen. Welcome to the Catch Me If You Can session related to security issues. My name is Cătălin Meiroșu. I'm a project development officer with Terena, and one of my multiple hats is to be the secretary of the task force Computer Security and Incident Response Teams at Terena. I see Carol in the back waving, so... Okay, our first speaker is going to talk about the NOAA project. His name is Spiro Antonatos. He's a PhD student with the Institute for Computer Systems at Fourth in Heraklion in Greece.
Oh, I have this. Thank you. Thanks for the introduction. And the next few minutes we are going to discuss about network of affine honeypots. In short, we call it NOAA. So in this presentation, we will discuss a little about the project and our work around honeypots. We will describe how we try to solve some problems using honeypots, and more specifically, the NOAA architecture and its two basic components, Argos and Honey at Home. And finally, we conclude. So some typical information about the project is a 3-year project started at April 2005, and it will end up at March 2008. It is funded from the European Union, from the Research Infrastructure Programs, and it consists of 4 work packages. Us in Fourth are coordinators, and at the bottom of the slide you can see our partners, DFNCERT, Alcatel, Vrije University from the Netherlands, Terena, ETH from Zurich, Fortinet, and Virtual Tree. So what is the problem we face? In a single word, we try to face malware, where malware can be defined as any malicious activity happening on the internet. It can be worms, it can be viruses, it can be keyloggers, spyware, everything. We see tens of them daily. They harm our internet life. And one thing we know for sure is malware spreads fast. Actually, it spreads faster than humans can react. For example, Slammer managed to infest thousands of hosts in a few hours. Latest advances have shown that worms can infect the whole internet in a matter of few minutes. So basically, we lack information about the cyber attacks. So this information is necessary in order to build effective defenses. And this is the goal of the NOAA project. So in NOAA, we try to gather and analyze information about the cyber attacks. Our final goal is to develop an infrastructure that will be able to detect and provide early warning for such attacks. And the technology we used is based on honeypots. So what is really a honeypot? It's a computer system that doesn't run any production service. In fact, it listens to an unused IP address space, and it is intentionally vulnerable to attackers. In contrast to our normal machines, it is closely monitored. In fact, it is heavily instrumented. So everything coming in and going out from a honeypot is monitored, and every activity inside the honeypot is also monitored. There are 2 basic types of honeypots, low interaction and high interaction ones. So briefly, low interaction honeypots are software components that emulate services. They can emulate a web server, for example, or a mail server. This emulation is usually done by script. The advantage of low interaction honeypot is that they're very lightweight processes. They can emulate thousands of IP addresses, and they are able to cover a large network space. But as they are based on emulation, the level of interaction they provide with attackers is very low. So in order to solve this problem, we use the high interaction honeypots, which in contrast with the low interaction ones, provide the highest level of interaction with attacker as they run real services. We can imagine a high interaction honeypot as a normal Windows or Linux system running out there. But high interaction honeypots are heavily instrumented machines. That means that every action that happens on them is monitored, and this makes them very heavyweight processes. And in fact, we need a lot of resources to run a high interaction honeypot. So what we try to do is, in NOAA, is that we want to combine the advantages of these two types and build a concrete architecture. So an overview of the architecture we have built looks like something, this figure. It may seem chaotic, but we will explain part by part what this architecture describes. As we see in the bottom of the figure, we have the NOAA core. It consists of low interaction and high interaction honeypots. For low interaction honeypots, we use HoneyD. HoneyD is the most popular and widely used system for low interaction honeypots. It is able to emulate thousands of IP addresses without problem. And the basic advantage is it is highly configurable and it is very lightweight. So in a few lines of configuration, we can emulate arbitrarily large networks, and we can define the behavior of all the virtual hosts to emulate. But inside the NOAA architecture, HoneyD is used as a filtering mechanism. So all the traffic that is not interesting, for example, port scans, SSH brute force attacks, unfinished connections, are filtered out by HoneyD. So all the other traffic which we consider interesting is forwarded to high interaction honeypots. So basically, the role of HoneyD is to offload our high interaction honeypot as much as it can, because as we said before, high interaction honeypots take a lot of resources. For high interaction honeypots, we use a system built by Vrije University called Argos. Argos is actually a virtual machine. It is based on the QEMU emulator, and it can emulate entire PC system. So basically, the key idea is that all data coming from the network should never be executed, should never be given to our processor for execution. So this is what Argos basically does. It tracks all data from the network inside our system. It tracks their path and all the actions happening to them. And in case that the data coming from the network are given to the processor for execution, it raises an alert. So that way, Argos is able to detect all exploits, either known or unknown, basically on the key property that network data are never executed in a normal condition. So an overview of the Argos is, we see that Argos is a middleware between the hardware and the operating system we monitor. So all the data coming from the network, from the NIC interface, is passed through the Argos emulator and are tagged. So in case that an application tries to use network data for execution, the Argos emulator stops the application and says, oops, we have an attack. So the data from the application and the network data coming from the network interface are correlated and are given to signature generation components. For all information, you can see at this URL. You can download, you can install Argos, you can play with it, and actually, it is very easy to install and configure. But so far, we have seen about honeypots, and the classical concept behind honeypots is that we have our unused IP address space, we deploy our honeypots, and we leave them there listening and waiting for attackers. But usually we have a limited number of honeypots, and this space is very limiting. So for example, in the NOAA consortium, we are around 10 partners, but we have only a few subnets available for honeypots. So this is not a very good way for fast and accurate results. So what we try to do in NOAA is to extend our infrastructure beyond the concept of classic honeypots. So we try to empower people into that process. And how we do this, we have built a tool called Honey at Home that brings Noah to the home users. You can imagine Honey at Home something like a similar project like SETI at Home, where people were helping for finding extraterrestrials. But here, we try to find attackers. So, what is Honey at Home? It's a lightweight tool that runs in the background of your machines, and it takes an unused IP address space, usually through DHCP. For example, if you run your Honey at Home client in this environment, you will take a free address, and it will monitor this address only. So all traffic going to that address will be forwarded to our central honeypots, our Honeybee honeypots, and our Argo systems. It needs no configurations, and you simply install it and run. And we have implemented it for both Windows and Linux platforms. At the bottom of the slide, you can see some screenshots of the installation procedure. So in action, you will see something like that. When it starts, it puts itself in the background. It creates a virtual interface. It gets a random MAC address, and it asks for an IP address from the DHCP server. So all traffic going to that IP address in the step 3 will be forwarded to our honeypots. Basically, the flow of Honey at Home is very simple. The attacker thinks that communicates with a Honey at Home client, but in fact, all the traffic going there is forwarded back to the Honeyd. After the filtering that the Honeyd performs, all the traffic is given to Argos, and Argos gives the appropriate responses. So the responses from Argos are following the reverse path. So the Honey at Home at the end will forward the response coming from Argos back to the attacker. So we have achieved two things here. First, attacker has the illusion that communicates with Honey at Home. But at the same time, we have captured all activities of attackers back to our honeypots. As we said before, Honey at Home is a free tool, and everyone can install it, everyone can download it and run it. But that includes that the attackers may also install the program and try to manipulate it and perform malicious activities against our infrastructure. So we have identified two challenges during the design of Honey at Home. First one is that the identity of both Honey at Home clients and our honeypots must remain hidden. In case that the identity of the clients is revealed, attacker can simply flood their black space, and this flood will lead up to our honeypots. The same applies that if the identity of our honeypots is also revealed, the attackers can directly flood it. We don't have any problem with false positives or false alerts because the Argo system is immune to all false positives and false alert. The problem we have is that as the honeypots, the high interaction honeypots are heavyweight processes, we don't want to flood them. The second problem we faced is that usually attackers maintain botnets, and botnets usually consist of thousands of machines. So we want to prevent attackers from massively deploying mock-up Honey at Home clients. And to prevent such automatic installation, we have used some widely used techniques we can find in web services like Hotmail, Yahoo, etc., where each user has to register, and the registration process involves CAPTCHA. CAPTCHA is this text down there where the site asks you, please fill in the text box, the text you see in the image. So every Honey at Home client has to register before it can use the client. For more information and software and documentation, you can find us at www.honeydhome.org, and the software will be available very soon, or you can contact us through the NOAA webpage. So far, we have talked about the classical setup of honeypots and honey at home users, normal users sitting at home and want to help us. Also, we want to involve organizations, institutions, public bodies that want to participate into NOAA. For those users, we have dropped some assumptions we have done about the normal users at home. And the basic assumption we dropped is that organizations that will formally participate into NOAA are trusted entities. So we have skipped all the anonymity we have embedded in normal Honey at Home clients, and this includes Tor, the anonymization network. And we have added some hooks, so administrators of the participating organizations can configure into Honey at Home the unused address space they own, and all the traffic into this unused address space will be forwarded back to our honeypot. So in a few steps, an organization can monitor its unused IP address space using the NOAA infrastructure. In the official NOAA site, you can find deliverables describing our architecture and the design of our components. And also you can find some software available. And apart from the deliverables, we have several conference papers and various articles and presentation in the ERSI news and in local press of various countries. So to conclude, in this talk, we described NOAA, a distributed architecture that tries to get advantage of the good properties of both low and high interaction honeypots. We have talked about two main components that form the NOAA architecture. This is Argos. Argos is a system emulator that is able to detect all exploits going into it, including 0 days exploits we have never seen before. Also in NOAA, we try to empower non-experts, home users, organizations that do not have the expertise to maintain and install honeypots to participate into this battlefield of cyber attacks. So through the Honey at Home tool, we have enabled unfamiliar users to participate into NOAA without any effort. Thank you for listening. Glad to hear any questions.
Thank you very much, Spiro. Any questions?
Is this an NOAA at Home client is Tor node too, or only Tor client?
It's only a Tor client, so it simply uses Tor.
Okay, and you have to emulate an application to be able to detect some attack on this application. What way are you using application to emulate? Are you using real applications?
We're using the application. Argos runs inside it normal operating system like Windows. So we run native applications. We don't perform any emulation.
So for example, what with commercial applications? Are you making an arrangement with companies, or are you buying this application? Or
so far, we have only built the prototype. This is a big problem. For example, you have to buy, for example, the Microsoft SQL Server if you want to emulate it. And so far, we have experimented with free software like Apache. And the problem is that you have to buy licenses even for your honeypots. But so far, we have seen that the most interesting attacks are not in commercial products. Of course, there is a category that deals with commercial products. But so far, what we have seen in our honeypots is attacks concerning standard services. For example, still we see attacks around the RPC service of Windows. We see still attacks that try to find open proxies and stuff like that. But the licensing issue is
so
a problem.
you are emulating Windows, but not Windows application running over the top of the Windows.
Yes, because we have license for Windows, but we don't have license for Oracle or products like that.
And what are your concerns about techniques to detect honeypots? Because, for example, if you are using Tor networks, Tor is adding a lag to a packet because you have to forward this packet through many Tor nodes.
Yes.
So, for example, attacker could detect this very high lag in response from the computers, especially if you can earlier ping the computers and the answer could be quite faster. For example, similar computer.
Yes, we are very familiar for this problem. It's a long discussion, and briefly I can say because Honey at Home runs into home computers, we have measured that sometimes you see lag in home computers even for no reason. For example, if you download a movie or you see some live streaming, that time you have lag. So sometimes the Honey at Home clients can hide behind this lag because of the properties that users already have some activity. In some cases, you don't. We have done some measurements, and you can find in our deliverables some more information. But there is a large area where home users show some lag because of their activities. And it's very difficult for the attacker to distinguish if this is a Honey at Home client or the client doesn't have bandwidth because he downloads or he sees movies or everything.
We have another question.
Yes, I have two small questions. The first one is, you take a virtual interface and you get a separate IP address to do your listening to. Doesn't that mean that you exclude almost all the home users because they will only get one public routed IP address anyway from their provider?
I'm afraid I didn't understand the question.
Okay, you ask a DHCP server for a new IP address,
Yes.
but almost every residential internet connector
Yes.
only gets one IP address from their provider. So doesn't this exclude almost all of the home users?
Yes. Usually what we do is usually ADSL users run behind a NAT network. That means there is a free address space there because they are in a NATed environment. For cable users or other users that simply take one IP address, Honey at Home cannot run there, of course. But especially in the country I am, all dial-up users and all ADSL users are behind a NAT environment, and they can take an IP address from there, and Honey at Home tries to configure the router automatically to forward traffic to that IP address space. But still, yes, this is a problem. When we started to implement Honey at Home, we originally designed it for small enterprises or normal users that are in universities and organizations where they can run the Honey at Home on their laptop. And then we extended it to home environments. But yes, of course, it doesn't work on all home environments, but in the majority of them, it could work.
Okay, thank you. The other small question, are you aware that hackers are actually taking the captcha pictures, putting them on another interesting service like downloaded movies they provide, and have third-party users actually fill in the captchas, so there's no real protection?
I didn't want to overload the slides with this. This is a classical laundry attack where you post your image in a website, promise content to the users, and they solve the image for you. But what we have done is that it is not a static captcha image, it's actually an animation. So you can consider it as a mini application. So because it involves animation and time, it cannot be forwarded to other sites. So users can solve it. You can see live demo at the website how is the registration process.
We have time for one more short question. Wait. Okay, then we go to the next speaker. While we are changing the speakers, one brief remark. Depending on the country and on the ISP, you may actually get, even as an ADSL user, multiple IP addresses. This is my case in the Netherlands, where I was allocated 8 IP addresses by my ISP without asking anything. So, surf snel. Okay. Our next speaker is Petr Kobierski. He's from CESNET, the National Research and Education Network in the Czech Republic. He's a master's student at the Technical University in Brno and a lead developer in the intrusion detection system at CESNET.
Thank you for your introduction. In this presentation, we will speak about developing of hardware-accelerated intrusion detection system, which we call the traffic scanner. Before I start, I would like to thank you especially to Jan Kořenek and several other people from LibreRouter team who did a really great work on this project. And a big thank you also belongs to CESNET, who gives a financial support to realize this project. At the beginning, I would like to outline the presentation. I will tell you something about the idea system. Then I will tell you why we exactly started with creating hardware acceleration ideas. Then I will present you architecture of our system and the achieved result. At the end of the presentation, there will be some future work discussed. So why we exactly started with hardware accelerated ideas? The multi-gigabit networks is becoming widely used. Most of you have got the gig network interface cards. Internet providers start to use 10 gig backbones and 40 gig Ethernet is knocking on the door. But we still have security problems. Some of this problem can be solved by searching some patterns in network traffic, which can tell us that something goes wrong. With this task, the intrusion detections like Snort or Bro can help, but this software-based solution cannot keep up with gigabit networks, as I show you later. As I mentioned, Snort is one of the most favorite software-based intrusion detection systems. It uses a rule-driven language for signature matching. Currently, Snort contains about 10,000 signatures, 10,000 rules. It's pretty much. Snort also contains several preprocessors which deals with IP and TCP fragmentation, and also there is a few preprocessor for anomaly-based detection. I would like to show you the typical Snort rule. The header part of this rule identifies the network flow. There is a protocol type, source network, destination network, source port, destination port. What is the most important of this rule is a keyword content, which contains a string which must be found in this network stream to be this rule triggered, and the alert is generated. Research shows that 80% of processor time is consumed by these activities, consumed by pattern matching. So the throughput of this software-based solution is limited to 200 megabit per second, as you can see on the following graph. We did this test with 256 rules. It means 256 strings, and we generate random traffic with 0.1% of malicious packets. All Snort preprocessors were switched off, so Snort do only the pattern matching task. As you can see, the throughput is about 180 megabit per second, then it's rapidly fall down, and Snort is absolutely unuseful because it misses almost all malicious packets. So we decide to accelerate this pattern matching task and create a hardware solution using the FPGA. How our system looks like. We've got here acceleration card from Combo 6 family and the host computer. The card is connected to monitored network, and it extract suspicious packets and send them to host computer. The extraction is done based on this SNORD rules, and in the software we do additional analysis using a standard IDS. I will later tell you why. Here is two possible network placement scenarios of our sensor. In the first, we are able to monitor 4 1 gigabit span ports, and the second connection is the traffic scanner is connected in inline mode, so 2 1 gigabit network lines can be monitored in a both way. The attacker has no possibility to find out that is being monitored. On the following diagram, you can see a system layer model of our system. At the bottom, there is an acceleration card with unique firmware. The card is controlled by our algorithm, the Ethernet driver, which map exported packet to user space. Thanks to this driver, the card is absolutely transparent to operation system, and it looks like any other network interface card, so it's no problem to use TCP dump and any other utilities. We use SNORD mainly to reduce a false positive, because in hardware we can't do everything like in the software. Another reason why we use SNORD is to get benefits from already created SNORD infrastructure. So we are able to use MySQL for storage alerts, use several engines for analysis, so we can create nice looking graphs and tables. So that was everything to the system part, and now take a look at the hardware, which is the most important part of our system. On the picture you can see our Combo 6 card. This card contains a Vertex 2 Pro FPGA, several static RAMs, content addressable memory, dynamic RAMs, and this card can be extended with add-on card with network interfaces. On this picture, there is a Software Pro add-on card with 4 SFP cages for gigabit Ethernet. We support Cooper and optics fibers. The card don't do anything without configuration, the FPGA, so some firmware is requested. On the following picture, you can see a block diagram of firmware. How does it work? From 4 network interfaces, we receive the packets to input buffers. Then the packet is read by header field extractor unit, which extracts some interesting fields from IP header, like IP addresses, protocol ports, TCP flags, and many other. These fields are used in a SNORD rules. The second functionality which do this unit is to mark the start of the payload, and in this payload the pattern matching task is done. The most important unit is a classification and pattern match unit. The classification units get the headers, do the classification, and send the results to pattern match unit. This unit, based on this result, activates searching some patterns, and if the pattern is found in the packet, then it's exported to software via PCIX bus. Otherwise, the packet is dropped. Here is some block diagram of a classification unit. We use on-chip CAM for IP and protocol classification, because in SNORD rules there is not so many IP addresses. There is usually wildcards as any, so it doesn't take so many FPGA resources. We map port and port ranges to prefix representation, and then we map it into the FPGA logic. Other fields like TCP flag, sequence numbers, and so on is solved by custom logic like comparators. The result from this unit is put together, and we get a bit vector when each bit denotes one rule, and if there is a logical one, it means that the pattern matching to this rule must be done in pattern match unit. The pattern match unit is the most important unit in our design. We use architecture with generic target throughput, so we can choose the target throughput. If we want to higher throughput, we consume more FPGA resources, and we can't put into the design so a lot of rules. So there is a dependency. And how this pattern matching works? We transform the strings and regular expression into the non-deterministic finite automata, and we do some optimization to reduce states. For example, for snort strings, we can do 50% state reduction using a prefix sharing, as you can see on the following picture. The classical NIFIA takes one character per each transition. It means 8 bits. So if we use 100 megahertz design, we get throughput only 80 megabits per second. That's not enough. So the processing more characters per clock cycle is requested. So we did a transformation to NIFIA, which we called extended NIFIA, and it takes more characters per each transition, so we can get, for example, 10 gigabits per second throughput. After the transformation to extended NIFIA, we map this automata to FPGA logic. The mapping is relatively simple. For each state, we create a flip-flop register, and the transition is realized using AND or logic gates. Maybe you ask why this hardware representation is faster than a software. In hardware, there can be more states active at the same time, so we do parallel searching for all strings at the same time. So that's why we get so high throughput. The pattern match unit and the classification units is hardwired into FPGA, so we must do a translation to hardware representation. That means we must generate VHDL sources, create run synthesis, place and route, creating bitstream, and loaded it into the FPGA. It's a really complicated task, so we've created a web interface which simplifies this process. So when the user wants to change the rules, he uploads it into our server, and we run the synthesis process, and after a while he received firmware for FPGA. The compilation time usually takes 10 up to 80 minutes. It depends on number of the rules. For example, for 200 rules, it takes 10 minutes, and for 1,000 rules, it's a little bit longer. Now we are getting to results. On this graph, you can see the relation between the FPGA capacity and the maximum throughput. We create several designs with different throughput. Here we take 1 character per clock cycle. Here 2, 4, and 8. So we can get this throughput, and here is a number of resources used in FPGA. So you can see that for a snort database, we can get to 4.8 gigabit per second. But in our design, we use only 3.2 gigabit per second because it's enough for 4-port gigabit card. Here is measured hardware throughput of our probe. We generate 2 gigabit traffic using a Spirent AX4000 generator. And as you can see, the red line is maximum theoretical frame rate, and the green is the measured frame rate. So we get to the maximum for all packet sizes. We also create several tests to compare snort with snort accelerated by our traffic scanner. So we generate this amount of traffic with this TCP UDP distribution. We put inside this amount of malicious packets, and with 1 gigabit per second we run this traffic to our combo card or in the software solution. The result is showed on this graph. The accelerated snort was able to detect 99% of all malicious packets, but the software solution was absolutely unuseful. We also try the real traffic test. We use only 100 megabit per second line, so the snort is able to analyze this traffic. Snort and the traffic scanner detect the same amount of alerts, so our solution works, but the traffic scanner was able to drop 99.87% of non-malicious traffic in hardware, so the software, the snort over the traffic scanner processes only 1 billion packets. The classical snort without acceleration processes to 1 billion. Now I would like to tell you something about our future work. We plan to create a network analysis and defense platform. This platform should work on 10 gigabit per second, and it should be useful for intrusion detection systems. There will be a firewall which can filter some non-interesting traffic. We plan to do some flow-based load balancing to software sensor, and there will be also some forwarding and blocking rules in hardware based on the payload patterns. If there's some place will be on FPGA, there is possible to put inside the sensor some custom application like DOS detection or flow analysis. So thank you for your attention. Any question?
Thank you very much, Petr. Any questions? Then I have a question. Okay. At some point during your presentation, you refer to the fact that you have to recompile the firmware if you want to download those new rules into the classifier. I was wondering what made you take this decision in the development process instead of programming some more generic traffic rule matching engine and then storing the traffic rules in some memory that you already have installed on the card?
We take this compilation because there's several approaches how to do pattern matching, but this approach has got really great results and is able to get to the highest throughput. Another reason, another solution where you are able to change the rules at the runtime is not so good as this, I think.
Okay, thank you. Any other questions? Okay, then we go to the next speaker. Thank you very much, Petr.
Thank you.
The next speaker is János Mohács from NIIF Hungarnet, the Hungarian Research and Education Network. János is the
So I will speak about design and implementation of an anomaly detection system that we are developed as part of the GN2 project, especially in the GRE2 activity. So what will be my presentation is basically 7 steps. First, why we developed such a anomaly detection, then a brief overview of NFSN architecture, and then anomaly detection and how it will be implemented in NFSN, then some operational experiences and future, and finally some conclusion. So let's look at the motivation. What the CHIRT teams, the computer security incident response teams are doing in their, for their constituency. Usually, when they detect some kind of abnormal behavior, either looking at the different traffic graphs or different measurement infrastructure, they are detecting some kind of peaks. For example, here in this graph, you can detect a peak, that one, for example, but it's not very visible. And also, there is another one over there. So you can detect visually. But you want to do some kind of more automatic way of detection, such as anomalies. And this abnormal behavior is usually detected, but you have to define what is abnormal. So that was important also for us. After that, you report and coordinate the incident and also act according to your processes. So the basic motivation was to somehow have this kind of detection here, because that one is not very easy to find. That one is quite easy. So let's look at briefly the architecture of NFSEN and NFDump toolset. It is developed at SWITCH, the Swiss Academic and Research Network. And basically, it's a tool for capturing and analyzing net flow data. I don't want to go much detail, but the net flow data is basically this kind of information, containing this kind of information about the whole traffic. So the NFDump is basically capturing this kind of information and storing in a database, and then NFSEN is taking their role and processing the data periodically and showing the results, and also storing some important data that can be presented in an RRD database. So let's look what can we do with the anomaly detection. Let's start with some kind of observation. Usually the traffic and flow pattern is showing some kind of periodicity. It's basically weekly periodicity can be seen, and also daily periodicity can be seen. And also we can see some kind of trends. So increase of volume of the traffic or number of flows. So that's important in our environment, that the traffic is increasing, but there are some periodicity. Also, we can say that the abnormal flow increase or abnormal traffic increase is usually some kind of deviation from the statistical pattern. We can say that it's some kind of abnormal, some deviation from the traffic pattern. So we can see some kind of peaks in the traffic pattern. So it is only, currently we are focusing only in this kind of deviation or abnormal behavior. And also, instead of processing again, so we already collected the information with NFSEN. Usually there are something similar system operated at every NRN and every network operation center to have some kind of information about the real traffic flow in their network. So net flow is already collected most of the networks. And also one important point in NFSEN that we already processed them by NFSEN, and we have the generated digested data in RRD databases. So the generated digested data is basically the protocols, TCP, UDP, ICMP, and unknown protocol, other protocol. And also it is generated per flow, per volume, and a number of packets also. So we have a large number of pre-generated, pre-digested data that we can use for statistical processing. And what was the need? Because of this observation, we need a forecasting method that can somehow adapt the seasonal and the trend increasing behavior. And what was our idea? To do some kind of alerting when the forecasted data and the measured data differs considerably. Okay. I don't want to go much detail, but some mathematical background of the selected forecasted method. It is called exponential smoothing. It was used in the economics quite heavily, this exponential smoothing. And there are several versions. The single exponential smoothing is very simple. What you usually say that you are predicting the next value by some kind of sum of the weighted previous data. And the weights is usually defined a following way, that you have an alpha value and the 1 minus alpha, and the sum should be 1 in most of the cases if the value would be equal along the path. So basically the formula can be written this way also because of this selection. And then you can also make a recursive formula. You can give the next prediction from the current measurement and the previous prediction. And also another easier formula for the next exponential smoothing algorithm, because there are several different versions of exponential smoothing algorithm or exponential prediction algorithm. That we are using is the triple exponential smoothing, and that is usually called Holt-Winters forecasting, that copes with the trends and also the seasonality. And this is the very similar, that is the similar calculation, where we have the component level, a component slope, and we have the seasonal components also. And these are the elements that you have to compute, and there are several parameters, alpha, beta, and gamma. That's one for the level parameter, one for the slope, the trends, and there is another, the gamma is for seasonal factor, how important the latest and how important the far past data, that is kind of information in the computation. What is important, that because it's a recursive computation, so all the parameters here, the MT, BT, and CT, can be computed from the previous observation, and then you can make it quite quick computation. So in one stroke, you can make the computation. So basically what is done, we have the existing NFSM, and we added some new elements here in the RRD database. And we are doing some Holt-Winters, this kind of computation is done. And also, if the forecasting error is too high, you can see some graphs here. How the Holt-Winters implementation was done. Luckily, the RRD tool has already have the Holt-Winters implementation. So, because it was already important when the RRD tool was developed, and the Web TV company developed, Jake Brutlag developed that extension for the RRD tool. What you have to know about this RRD tool and Holt-Winters prediction parameter, Holt-Winters extension? The computational parameters are stored in a RR round-robin archive, and it is usually computed for each primary and secondary data elements, data points, sorry, according to the RRT tool terminology. So these parameters are stored in the RR archive. So creation is quite simple. You have to define that you have a new RRA, and you have to specify your array length, basically how length you want to keep your data, how long you want to keep, alpha and beta, because that's important for the prediction. The gamma you can't define. There are some definition that you can use gamma quite easily. So it is used according to the books, the recommended values. And also you can define the period that you have to use. Often you have the period time in your system. And also the other parameters that is important for the Holt-Winters prediction can be modified by the RRD tool tune extension. Also the positive and negative confidence interval and the failure threshold, number of consecutive errors in the prediction that you want to use to generate a real failure in that element. So what is our current setup? We are using NetFlow data, about 40 routers, and we are collecting this data facing only for the customers, so the universities, research institutes. Sometimes we are collecting from all interfaces because the router doesn't support interface per interface NetFlow collection, so that is a kind of limitation in the current software. And what was our observation? That we are collecting full NetFlow from these routers, and it's approximately 50 or 80 megabit per continuous traffic towards to the NetFlow collector. We have several 10 gigi lines and several gigi lines. Because we are just collecting the NetFlow information, basically the headers of the traffic, we have quite good compression ratio, if I would say. And currently we are not collecting those devices which is supporting only sampled NetFlow. The reason is that we cannot really correlate and handle properly the volume of the traffic, so it is not really relevant for us, so we prefer to have a similar one. So maybe what we can do to make sampled NetFlow from all machines, but sometimes full NetFlow is better for analyzing the traffic. The NetFlow collector is basically a server with 2 processors, with 7 processors. We have a large amount of memory, and also we have quite large amount of disk for just this purpose. And we are using auto over Ethernet for that disk. That means we are connecting devices, the disks, a special device called auto over Ethernet device that all the ETA packets, the ETA disk access packets are converted to Ethernet packets. So the operation point of view. So testing, we did a separate RRD updating. If we are looking back to that one, basically what we do, we are replicating this database. We are keeping the original RRD database, and also we have another process. So we are running to NFSen from these data. We are using this capture data for one normal NFSen operation and another for this whole winter prediction. To have some visual detection, we generating a special graph and then from that graph we can list quite easily the abnormal behavior. For example, we have an example here a few days ago. That is the capture, and you cannot really see that there is some peaks somewhere here, but here the aberrant behavior detector, you can see that there was some problem here and here. And let's click on that one, and then you can see that there is some peak. Now you can see the peak. And finally, you use the NFSen built-in, the peak finding setup. You will find the real peak in the NetFlow graph, and then you can see quite easily which router was so it was from that router, and also after going down to the NFSen interface, you can dump the whole packets, what's going on. And according to the observation, I somehow anonymized the data. So it came from that machine, and if you can see, it's increasing the source port number, and it is scanning some or trying to attack a certain machine via port 80. And then you go for the incident handling. So we have we are starting with incident handling and trouble ticket system. What is detected? Some kind of assessment from operational practice. Currently, the tool can detect different kinds of DOS, denial of service attacks, and also probing types of attacks, viruses, worms, and so on and so on. But if we want to classify the different kinds of attacks, we cannot attack kind of remote to local attack. That means somebody want to able to log in to a machine or access to other system that is not authorized to him or her, or maybe user administrator attack is not possible because we don't have the backend content. So we can only detect that kind of attacks. Also, we can see some false positives. Sudden decrease or increase of traffic. Also, decrease of traffic can somehow generate some kind of errors. So, for example, there was an outage here, and it's not exactly that one, but because it's a weekly, and this is not a weekly data. But when I take these pictures, I'm pretty sure that was the mark. So it is detecting the outage, starting of the outage, and also the coming back of the traffic detected. So that can be also detected. This is not the purpose of the tool, but because of the statistical behavior and automatic behavior of the Holt-Winters algorithm, it will be also detected. Sometimes we have false positives because of start of university terms, because students are registering for certain courses remotely, and 10,000s of students are starting to use web servers suddenly in a few days time. Then the traffic will be increased considerably. Also, we can detect sometimes remote data backup on the network. What about the future. We need some further investigation. The actual settings of alpha, beta, and gamma. We currently use the recommendation from statistical books. So these are the alpha and the beta. So 0.1 and 0.035. These are the recommended for most of the data, but probably not suitable in every situation. Gamma is automatically can be calculated from some kind of information, especially from the period. Also, we tuned the following way that the confidence interval, the positive confidence interval is 5 times the deviation, and the negative is 10 times the deviation. So to avoid traffic decrease alarm, however, we still have traffic decrease alarms. We selected a weekly setup. We don't know whether it's better to have daily or not. And unfortunately, the biggest problem of the hot winters detection that you need 1 week or even more data to start the prediction, because they have to calculate all the parameters, all the historical data has to be there to be able to calculate and have some kind of useful information. And that requires plenty of this space. Of course, you didn't need all data, but for example, the 2 terabyte data that we have, it's basically 2 weeks of data. And probably we have to also correlate with other anomaly detection system. Also a feature that the NFSEN has a new version. Currently it's not officially yet. There is a snapshot version. 1.3 or 1.4 will be there, which is a new channel-based architecture that allows more flexibility. Profiling, I didn't mention profiling, what is profiling an NFSEN, but basically a kind of filtering of your data, and you will store that data also differently. But here in the channelized architecture, you can reduce the amount of data with profile filtering, and then you can combine the data somehow, and then it allows you some more flexibility. Also, shadow profile is possible, and a kind of IP lookup. So if you go for a certain over a certain packet, then you can see the owner of the packet, the owner of the IP. That's a very nice feature. So we will adapt this NetFlow, this hot winter anomaly detection to the new architecture. It requires considerable changes in the code, because it is also rewritten the NFSEN. And another important future development that you might remember that it was not completely automated, the detection. You still have to go through the different graphs. You could see there was some color dots on the abnormal behavioral graph, and you had to click on it, and then you have to see what's going on that point of time. In the new NFSEN, there is an alert feature that you can define a certain condition. And these conditions are usually the original NFSEN that has only kind of information that number of flows that you can do some kind of detection. But here we are planning to introduce a new option. If the hot winter will detect something, then you will have an email. So you will have automatic alerting, you will have alerting via email or other way, maybe calling another plugin. So that will be also included in the next version. So concluding or finishing my presentation, we can say that this whole winter anomaly detection is working quite well. Unfortunately, it requires quite lots of disk space. We are happy with NFSEN and NFDump. And also, this whole winter anomaly detection helped to establish some early warning system for us. We don't have to wait for report from other networks that there was some hacker activity took place or some virus activity took place in your environment. We can look at earlier than we had the report. That also somehow improved our CCERT operational practice. But unfortunately, it requires modification of the original NFSEN. And unfortunately, this is not quite easy task. The NFSEN is not very modular. There are some extension capabilities of the NFSEN using via plugins, but plugin is not enough for this whole winter detection because you have to modify the RRD database. And some further information, and if you have any questions, I'm willing to answer it.
Okay, let's thank the speaker. Any questions?
Maurizio.
Just a quick comment. You mentioned that I think that the database, the RD database feature of the whole winters is not the most important one. The algorithm itself is the most important feature. So I strongly support your plan to write a backend plugin for Holt Winters, which is totally decoupled from the current implementation, which is also feeding the database. I think that if we have this backend plugin in NFSEN, is more than enough for enhancing the current detection capabilities of NFSEN. So basically, in my opinion, you can throw away the current implementation or just implement the Holt Winters algorithm as a Perl module in NFSEN, and this is a great step forward. This is my personal opinion, of course.
A kind of answer for that one. I think there is one option. We are investigating that option also, but it seems that easier to add and modify the RRD database because the RRD tool already have this whole winter detection. You can implement in a plugin, but if you're implementing in a plugin, you have to process twice the data. Probably it's not a big issue for the RRD database because the RRD database doesn't have so many data that you have to read and process again. So maybe that's another option. But for efficiency reason, it's better to add in the RRD database itself because you can make the calculation when you store the data.
Okay. Any additional questions? If not, let's thank the speaker.